Okay, Assalamualaikum warahmatullahi wabarakatuh and very good day. So today we're gonna go through a new chapter or new still chapter 2 but new topic which we're gonna go through how to construct Magnel diagram and also tendon profile. Okay, there's two main topic outcome for this subchapter, which is first, student must be able to construct a Magnel diagram at the end of this course and also able to produce tendon profile design. Okay, construction of Magnel diagram. So basically, if you can see in this slide, you can see equation 12, 13, 14, and 15. So all this, all this equation is actually mathematically formed from equation 1 to 4 previously that we have gone through, and also equation 5 to 8. Okay, so with this equation being rearranged and then mathematically, so by considering your p naught in the form of 1 over p naught to the right side as a mean parameter, and all other parameters such as area, pre-stress loss, moment, the stress limit are all being put on the right side. So then you will have four inequalities equation. So basically, when you have these four inequalities equation, you can determine what will be your range of your pre-stress force with the range of eccentricity. So you have two unknown here, your pre-stress force and also eccentricity. If you don't use, Magnel diagram, your calculation in finding especially the pre-stress force will be very tedious and repetitive because you have to try and error one values after another values, the eccentricity value. So basically, if you use, Magnel diagram, means you treated it graphically. So your calculation in terms of finding or getting your range for pre-stress force will be much easier. Okay, this slide is showing you, the previous slide that we have gone through, which is equation 1, 2, 3, and 4, which, we already indicate what will be the value of our limit stress, at service, at transfer, and so on. While this slide, our previous inequalities equation, from 5 to 8 that we have, kind of like formed from equation 1 to 4. Okay, so basically we have gone through this, previous lecture as well. Okay, one thing you have to take note, all equations that we form here, the four inequalities equations, is actually linear relationship, means that you're going to get a straight line for all equations, okay? So what we can say is, Magnel diagram is a very powerful design tool which covers, all possible solution for all inequalities equation that we have. Okay, so it will enables a range of pre-stress force as these values to be investigated. You will get the range of pre-stress force and eccentricity. So values of minimum and maximum pre-stress force can be readily read and also easily to be determined, right? So it kind of like, it could show you what will be the minimum pre-stress force and what will be, correspond to the maximum eccentricity and vice versa. So basically, when you have, as your eccentricity is reduced, your pre-stress force must be increased to compensate. Okay, so that kind of like relationship that you will see later on in the Magnel diagram. That you have to also take note the signs of inequality. If you follow the mathematical rules, it could be reversed, especially for equation 13, to account that the fact if the denominator is negative. Okay, so you have to be aware of the denominator values, the bottom part of your equations. So the line 1 to 4, okay, in your Magnel diagram, is actually correspond to equation 12 to 15 that we have mathematically rearranged from previous equations. So, and you will see in minor diagram as well, there is what we call as line 5, which is represent the physical limitation of the maximum eccentricity. So what is physical limitation is actually when you have a physical limitation, it could be like some limitation to the position of the tendon that you want to place, maybe due to your beam pre-stressed beam cover, or the pre-stressing bed position and so on. So it could be any constraint that it might occur during during construction or during your pre-stressed beam design that you want to design. Okay, this slide you will see that how generally Magnel diagram can be constructed. So you will have well the y-axis, which is 1 over p naught, and then x-axis will be represent the eccentricity value. So you will have like first equation 1 being drawn, a straight line, linear line, then you have equation 2, equation 3, and also equation 4. So all this equation 1, 2, 3, 4 is following equation 12, 13, 14, and 15. So the fifth line, which is the physical limitation, is where you put one line to represent any constraint that you might have for your eccentricity. So with this bonded of 5 lines, you will see that the yellow area is being colored yellow. So that will be your what we call as a safe zone, right? So that the range of your pre-stress force and your eccentricity should be in that boundary. Okay. Now let's try to construct a real Magnel diagram from actual properties that we could have, or the properties that we have calculated before in example 3. So this is taken from example 11.5, mostly Bangi both. So in this slide it is called example 6. Okay, so what is the question is construct a Magnel diagram for the beam given example 3 and determine the minimum and maximum values of pre-stress force. Okay, assume a maximum possible eccentricity of 125 mm by allowing for cover and etc. to the tendons. So the properties from example 3. Okay, so you can see the red box here is actually all the properties that we have determined before in example 3. Okay, so we will use first equation, which is equation 12, as you can see in the slide, and then we just kind of like substitute all the parameters, the k value, the a value, the area value, the zt value, the stress maximum, moment maximum, and so on. Okay, so just aware of your your parameter, changing your parameter and so on, because it will affect your values. Okay, so you will end up with in a form of 10 power of 6 over p naught, which is bigger or equal to 1210 minus with 20.77 eccentricity, or e. Okay, so if you look into the form of how the equation is being written here, so you will see that there is 10 power of 6 over p naught. So it's better when you construct your Magnel diagram, you leave it in this kind of form, 10 power of 6 over p naught. So that is equation 12. Then you will do, or you will calculate the same thing, the same way, by considering all the parameters, plus, minus, and so on, for the other three equations, which is equation 13, 14, and also 15. You see equation 14 and 15, that have been calculated and been put. So please recalculate this equation back. Make sure that you are getting the same values as what in this example. So once you have, later on we will see one by one how to construct the Magnel diagram. But here the answer is whereby you will, at the end, you will get what will be your maximum, 10 power of 6 over P naught, which is equal to 2415. But then it will give you the minimum P naught value, which is 414 kilonewton. So when you get minimum 10 power of 6 over P naught, which is 862, which will give you maximum P naught, which is 1160 kilonewton. So you later we will see in detail how you get this value. Okay. In this slide, you can see that the value of uh, every equation 12 to 15 is being tabulated here. So how you want to construct your Magnel diagram is, first you must have this table. Okay, you must have this table where it started with having the E value, the range of E. You determine first, you kind of like decide what the range of E that you want to consider in this Magnel diagram. So as you can see in this table, so I have select like minus 60, minus 40, minus 20 to the 140. So you will see the range of 20, 20, increment of 20 here for the E value. So the E will represent the x-axis value. So then with the range of E that you have stated here in this table, so you will be able to calculate what will be your values for 10 power of 6 over P naught, which is your y-axis value. So for each equation having different equation 12, 13 and 14 and 15 definitely will give you different value for your y-axis. Let's have a look how we want to construct a Magnel diagram. So after all the values we have tabulated in the table in previous slide, which is you have all the E range with the respective value of your 10 power of 6 over P naught. So what you have to construct first is you get a graph paper to make sure that you're going to get accurate values for each of the parameter. So then you're going to construct like the x-axis and the y-axis. So the y-axis is for 10 power 6 over P naught, and the x-axis is for eccentricity range, which you have determined in the table between minus 16 to 160. So it can be in any range that you want to put, because as long as you will be able to capture the boundary of these four lines, because it could fall, as you know, when you have what we call that coordinate in the graph paper, you will have four quadrant, right? So you must aware that in which quadrant actually your boundary will fall. Okay, you have to draw your boundary. Is it in the first quadrant, or in the second quadrant, third quadrant, or fourth quadrant? So then you once you know where, then you can enlarge the scale and determine the right scale for your graph. Okay, so now what you have to do, then you start to plot the line according to the data that you have tabulated before, the E value, and also the equation 12, equation 13, equation 14 and 15. So you have first line equation 12, second line 13, 14 and 15. So once you plotted all the lines, so basically what you will get is the permissible zone. Alright, so you will get the boundary region where it's bounded by these four lines. So these four lines is where the yellow color here, okay, so it's called permissible zone. So with this line, you'll be able to determine where is the maximum point and where is the minimum point. So the maximum, what we call that, you go to the lowest point of your boundary. So the lowest point of the boundary will give you the minimum values of your 10 power of 6 over P naught. So this 10 power of 6 over P naught is actually represent the maximum economic pre-stress force, okay, which is, if you look into the calculation, the minimum 10 power of 6 over P naught is equal to 862 Okay, so with 862, it will give you the maximum value for your P naught, which is 1160 kilonewton, with respective eccentricity is equal to 17 nm. Okay, so next, once you get the lowest value of your 10 power 6 P naught, then you go to the maximum value of your 10 power of 6 P over P naught. So the maximum value of 10 power 6 P naught is actually 2415. So when you recalculate back your maximum value, it will give you the minimum value of your P naught, which is equal to 414 kilonewton. Okay, and then with, of course, the respective eccentricity value is equal to 121 mm. So then don't what we call that, don't forget as well, your the fifth line, which is your physical limitation, which is in this question or in this example given E maximum should be 125 mm due to the cover of the beam. So, and then when you plot 135 mm, you will see that the boundary is, didn't reach the line of 125 mm. So, means that your equation is okay. Your boundary is not affected by the physical limitation line. Okay, for this slide, I provide you the past year question, June 2018. So, I want you guys to try this question, especially 3A. Whereby you need to construct a Magnel diagram. So I want you all do this and then submit this, okay, by next week, okay, during our lecture, 2 hours. Guys, next is where we want to learn how to construct a tendon profile, alright? So what is actually tendon profile? So tendon profile is actually kind of like represent the behavior of the tendon. Okay, so the behavior of the tendon generally can be a straight line, or it also can be a parabolic shape. So normally when you have normally parabolic shape or function, we use it when you want to design tendon profile for post tension beam. Okay, because post tension is where you're going to have the functions, and then the tendons are used to provide forces to the structures. Okay, so where the behavior of the tendons. So cable is denoted as the resultant of all individual tendons. So each one line of the tendon, represent in the profile is representing one cable, okay, one tendon. Right? So in the graph or in the figure down, you will see a straight line. So you will see a dotted red line there, along the length of the beam. So that normally represent the neutral axis of the beam section. Okay, and you will see the second line is where the second figure is whereby the parabolic tendon. So you will see there is a kind of like a deflection. At the end, both end of the beam, you will see that the eccentricity is 0, and then at the midspan, then you will see the maximum eccentricity values. Tendon profile parabolic function is whereby you will have like the profile of the tendon is curve or is parabolic. Okay, so the function that you use is the parabolic function, or what we call as parabolic function, which is y is equal to ax squared plus bx plus c. Okay, in our case. So generally, if you look into the figure provided, so the distance from the distance from the neutral axis at the midspan is equal to a, and at the end span is equal to 0. Okay, then we can also say here that when the x is equal to 0, which is there's no slope or there's no value for the y, which is y is equal to 0, and then it will give your c is equal to 0 for equation y is equal to ax squared plus bx plus c. Okay, and when the slope at 0, 0, we can conclude is equal to 0. So when you differentiate the equation, the parabolic function equation, so you differentiate dy over dx, so you will get 2ax plus b, which is equal to 0. So the slope normally represented by the differentiation of dy dx. So when, therefore, dy dx is equal to 0 will provide you or give you b is equal to 0. Alright, so you will end up with b is equal to 0. Okay, so but when you put or you use x is equal to L over 2, which is at the midspan, and then we know that the y values there is equal to a. Alright, so then you can conclude that a, the capital A in the equation of parabolic function, now you can conclude is equal to for a small a divided by L over 2. Okay, try to rearrange this equation so that you will get the sense of how to get the equation for the parabolic, which is you will end up with y is equal to 4ax squared over L power of 2. So normally when we want to construct a tendon profile, so we we kind of like already determine the value of pre-stress force that we want to apply to our beam. Okay, which of course pre-stress force, the inequalities equation that we consider after satisfied all the critical section. So then we will construct the tendon profile in terms of to determine what will be the eccentricity at which this force must be provided. Okay, because we are not only consider the critical section of it, but also we have to consider the condition of the length of the beam, throughout the length of the beam. Okay, and at any section along the member, so E is the only unknown term in the four expression, and this will yield two upper and two lower limits, which must all be simultaneously satisfied. Okay, so you will have kind of like one unknown here, which is your E, and then your P is already determined through your Magnel diagram. So this requirement must be met at all sections throughout the member and will reflect both variation of moment, preset force, and also section properties along the member. Okay, so we remember our four inequalities equation that we use for our Magnel diagram, which is equation 12, 13, 14, and 15, where we have the main parameter 1 over p naught, which we rearrange mathematically. Okay, and then we put it as a main parameter to the left side, and then the other parameter on the right side. So the thing with when you want to construct what we call a tendon profile, so then you have to rearrange back the equation. All right, so rearrange back the equation, and then you have to make like your E as your main parameter, which is you take the E and then bring it to the left side, and then all other parameter you bring it to the right side. Okay, so then you will have the equation in terms of other parameter, and then you will get the value of your E that you want. So generally this will you will form four equations, okay, in terms of E as your main parameter, which is equation 16, 17, 18, and also 19. Okay, one thing also, and one thing that you might want to take note is the values of your moment. Okay, the values of the moment will change depending on where is the location of E that you want to find. Okay, for example, throughout the length of your beam, okay, if say that your E position of your position of the length of your beam is at the end of the span, so you might not get your moment might be equal to 0. And then if say that your for the position of your beam is at the mid span, then you will get probably your maximum moment, bending moments at the midspan. So the values of the moment is actually really depending on your bending moment diagram of your beam. All the equations, right? So you have to evaluate all equations at any section throughout the length of the beam to determine the range of eccentricity within which the resultant force P naught must lie. Okay, so that's what you have to, basically do in developing the or constructing the tendon profile. So moments like moment maximum, moment minimum are those relating to the section that you consider. So for a member of constant cross-section, which is you have from end to end, it's the same. If minor changes in pre-stress force along the length are neglected, the term in brackets in the expression are constant. It will become constant because it's the same. So therefore, the zone within which the cyclop must lie is governed by the shape of the bending moment envelope. So as you can see in the figure below. So figure below is say it represents for cable zone limit. They just give you example of two equation here or two tendon position here. Okay. So first, what you have to do, you will have like the beam, a beam, with the line cross section, and then you will have you have to draw where is your central axis, your neutral axis of your beam. Okay, then you will start to have like a first line of the equation, then you have one profile or one tangent profile. Okay, will give you the distance from at the midspan, which is from the line, the green line, the top one, to the tangent profile, m maximum over k p naught. Okay, and then you will have a second line which is at service. When you have then you will be able to draw the second tendon profile. Okay, then the distance between that line to the tendon position at midspan is where we have m minimum over p naught value. So the range will change depending on the moment values. Now let's have a look. Example 7, this example is taken from example 11.6, mostly Bangi et al. 2007. Okay, so in this example where we need to construct a tendon profile. Okay, so please take note all the properties, the values, the parameter used in this example 7 is still the same parameters that we used in the previous example. Okay, so it's the same parameter, right? So determine the cable zone limits at midspan and ends of the member designed in previous example for a constant initial preset force of 700 kilonewtons. So please take note here, whereby in terms of constructing tendon profile, one must already determine what will be the pre-stress force value that you want to apply to your pre-stress beam. Okay, so you will have four inequalities equation in terms of E as your main parameter at transfer and also at surface. So if you look what I've done here is basically I calculate earlier each parameter in the because you can see that for each equation the values the parameter values are repetitive. Okay, it's the same thing. The different will be only in terms of the sign. The sign might change, instead of plus you get minus and so on. So for equation 16, 17, 18 and 19. So it much to me it is much easier easier to calculate it like this. Okay, rather than go one equation by one equation. So once you have all the parameter being calculated, okay, so now you consider the position of the E, right? So first, for since that the profile that you need to construct, as what mentioned in the question, you have to consider end and also mid span of the beam. Okay, so you have to consider one by one. So in this case, they consider the first condition, which is at the end of the beam. So what happened at the end of the beam, you will see that the values of the moment, all right, is equal to 0. So you have, for example, equation 16, you have your eccentricity at transfer lesser or equal to 58.29 minus which is plus 5.83, okay, in bracket, plus with 0. Okay, the 0 means that the moment at the end of the beam is equal to 0. So is equal to the total of equation 16, the E is equal to 64.12 mm. Okay, and then you will calculate every equation, one by one from 16, 17, 18, and also 19. Okay, so in terms of to fulfill all the four inequalities equation, you will see that what we call that the E uh, lie within the range of 35 mm in this case, okay, where it fulfill all the four inequalities equation. Okay, so next is where you have midspan of beam. Okay, at midspan of the beam, so you see that the moment values, the moment parameter values is not no longer zero because you have moment at the midspan of the beam. Okay, so at transfer for equation 16, 17, and 18, 19, you put every parameter, substitute on all parameter that you have calculated before, and then you will end up with values for your E for each equation. So the conclusion that from these equations that you have calculated, you can see that the eccentricity at midspan is lying between 47.8 to 66.26 mm. Okay, let's take a look on how we want to construct a tendon profile. Okay, so first of all, for to construct a tendon profile, of course the best is to have a graph paper so that you will get accurate values for the position. But then if you don't have, then of course you have to just scale it on a regular paper. Okay, so then the first thing that you must have is actually, of course, the beam line. Okay, the beam line cross section. Okay, then you have to plot on the left side the range of the position of your eccentricity. Okay, by taking into account the 0 0 position from end to end length is the position of your neutral axis or your central axis, okay, of your section, of your beam section. So then after that you will start to draw the end value or the end span value of your eccentricity first for each equation that you have. Right? So first you will have in my case I draw equation 18 first, right, the green one, which is considering the end values of your eccentricity, a straight line. So then you will have equation 19, the end span value of your eccentricity. You have equation 17, which is the purple color, and then also equation 16. So you have all straight line first. Okay, then you will start, you draw the midspan line. Okay, the midspan line is whereby along the length of the beam, where is the midspan point. Okay, so once you have drawn the line, so then you have to determine what is the the one that you have calculated before, the eccentricity value at midspan. Okay, for every equation. Alright. So for equation 18, which is the green color, I put it there, a mark of the dot, the green dot there at the midspan for the equation 18. Then the red dot will be for equation 19. The purple dot will be equation 17, and the yellow dot is for equation 16. Okay, and once you have the four dots representing all the four equation, then you will start to draw a curve, connecting from end span, passing through the midspan dot, and then you continue to draw it to the other end of the beam. So you will get like a curve there. Okay, like a curve. So the line, the green line represent for equation 18, the red curve will represent for equation 19, the purple one equation 17, and the yellow one equation 16. So you have four lines representing four inequalities equation here for this tendon profile. Okay, so in this case, what you need to aware is the boundary, because these equation are inequalities equation, greater, lesser, and so on. So you have to consider that as well in this tendon profile. So once you consider that, you will know where is the boundary that fulfill the four inequalities equation. So in this case, the boundary will be lying on the between equation 19, which is the red line, and also equation 17, which is I marked there as a yellow boundary color. Okay, so and then you will have the position of the equation 19 to the lines will be moment maximum over k p naught, which is equal to 106.07 mm, and the moment minimum from the curve of your equation 17 to the straight line, which is 31.9, okay, mm, right? So here we go. So you get the range of your what we call that, of your tendon profile, and then we know that the boundary is bonded between equation 17 and also equation 19. So the midspan values that you can conclude that the E will be in a range of between 47.78 and also 66.26. Okay, so that will be the range that you get from the tendon profile. Try and look back at your Magnel diagram that you have constructed before. Okay, so in this Magnel diagram, basically if you plot it back, your range of your E that you get from your tendon profile, for example, you mark in your Magnel diagram, your range of E is equal to 48, you round the number, of course, 48 mm, and then of course another range, the maximum range will be 66 mm, and then you drag it the line, okay, you drag it the line to the y-axis, which you will get the P naught value is actually 700 kilonewton. It's the same P naught value that given in the question for this example. Okay, so and then you will see as well, the position of the E is actually fell in the boundary, okay, of where the permissible zone of of what you have constructed in your Magnel diagram. So it kind of like give you the what we call the definition of the similarity, because you are using the same equation, inequalities equation, for Magnel diagram and also for the tendon profile. So you should be end up with the same values, the same range, means the range is still considered in the Magnel diagram as well, whatever range that you have determined in your cable tendon profile. Okay, so width of the cable zone. So basically from the Magnel diagram, so with any chosen value of your pre-stress force, there is eccentricity range, okay, which where you're gonna get a resultant tendon force must lie. So as the force approaches a value corresponding to the top and bottom limit of the diagram, the width of the available cable diminishes until at the very extremities the upper and lower limits of eccentricity coincide, which is give zero width of the cable zone. So basically, a pre-stress force will be chosen which has a value in between upper and lower limits of permissible pre-stress force. Whilst at the same time enduring that for the chosen force, a reasonable width of cable zone must exist. Okay, so don't forget the requirement of cover, minimum spacing between tendons, available tendon size, etc. must be considered when you determine the width of the cable zone. Okay, so basically you could also conclude that Magnel diagram will give you a range of alternative can be quickly considered without necessity of any further calculation, because you can simply plot it in the diagram itself in terms of knowing what will be the range of your E that you want to use with what will be the respective pre-stress force that you want to apply. And yeah, that's all for today. I mean, for today's lecture, which we try to cover on how to construct Magnel diagram and also tendon profile. So I hope you guys are clear by now, but of course you need more exercise, to understand this topic clearly, and be able to do it yourself and so on. Okay, more exercise is definitely needed for this topic. Okay. I think that's all from me, and what we call that. So we will continue with our next lecture next week. So please don't forget the tasks, the past year tasks that you have to read, you have to do. Okay, and yeah, of course, because more practice, then you will be able to understand this topic, better or much clearer. Okay, so I think that's all. Thank you very much, and thank you for your attention.